Welcome back, everyone. Today we're diving into section 21.2 of your software engineering syllabus, and I'm super excited to guide you through this explainer on architectural patterns for real-time software. If you've ever wondered how the code you write actually interacts with the physical world, how a car knows exactly when to pump its brakes, or how a burglar alarm instantly reacts to a broken window, you are in exactly the right place. Today, we're really establishing why real-time embedded systems are so absolutely crucial in modern software engineering.
Here's our agenda for today. We'll start with real-time software architecture, then move through Pattern 1, Observe and React, Pattern 2, Environmental Control, and Pattern 3, Process Pipeline. Then we'll tackle exam focus and combinations, and wrap up with a summary and next steps.
Section 1. Real-time software architecture. Process-oriented design.
To start off, we really need to build a strong foundation by understanding how real-time architecture is just fundamentally different from what you already know. If you've mostly been building desktop applications or web apps up until now, your brain is probably hardwired for object-oriented design, right? You think in terms of classes and objects interacting at their own pace. But in real-time embedded systems, we have to completely flip that mindset. These systems are strictly process-oriented. What does that actually mean? It means we care about concurrent, parallel processes communicating with each other. Why? Because an embedded system has incredibly strict deadlines for responding to external events. A late response isn't just a minor glitch. In a real-time system, a late response is a total system failure.
Before we get into specific examples, let's nail down an important definition: architectural pattern. An architectural pattern is an abstract, stylized description of good design practice. Think of it as a blueprint capturing expert knowledge on how to organize your system. But, and this is a really crucial point, it's a starting point, not a rigid template. If you just copy and paste a pattern without thinking about it, you'll probably end up with a highly inefficient process architecture. You always have to optimize the pattern to make sure you don't have a bunch of unnecessary processes eating up your system's memory and processor time.
Section 2, Pattern 1. Observe and React. Monitoring systems.
Okay, let's dive into our first major topic, which is a highly testable concept for your exams: the observation and react pattern. Looking at this structure, you've got an observer process right at the front. It routinely collects and monitors data from a set of sensors, and then passes those values to an analysis process. Most of the time, everything is totally normal. But if that analysis process detects an exceptional condition, something out of the ordinary, it reacts. It triggers a display process to notify an operator, or it sets off an alarm process, or it might even fire up a reactor process to take immediate preventative action to minimize the damage.
Let's ground this with the burglar alarm example from your textbook. Imagine a commercial building. The system uses all kinds of sensors: movement detectors, door sensors, window sensors, even a voltage monitor. The system is continuously observing these sensors. If an intruder forces a window open, or say there's a sudden 20% drop in voltage, which could mean the intruders cut the power, the analysis process catches this instantly. The system reacts right away by switching to battery backup, sounding an audible alarm, turning on the lights in that specific area, and automatically calling the police using a synthesized voice. That is Observe and React in action. So, just to recap, Observe and React is all about continuous monitoring, looking for exceptions, and triggering alarms or displays when they actually happen.
Section 3, Pattern 2. Environmental Control. Active System Actuators.
Moving on to our second pattern, we're stepping beyond just observing our environment and moving into actively changing it. To really grasp this pattern, you absolutely have to know what an actuator is. I want you to burn this definition into your memory. An actuator is a physical hardware device, controlled by your software system, that physically alters the system's environment. While a sensor reads the environment, an actuator changes it. Think motors, valves, hydraulic brakes. Those are actuators. And the ability to physically change the environment using these actuators is exactly what separates the environmental control pattern from the simple observe and react pattern we just talked about.
Notice how the flow is a bit different from our last pattern. A monitor process receives the sensor data and feeds it straight to the central control process. The control process makes a decision based on that data, and then, here's the major difference, it issues explicit control instructions down to an actuator driver process. It might also have an actuator monitor process feeding data back up, creating a feedback loop just to ensure the actuator actually did what it was supposed to do.
A perfect way to understand this is the textbook's anti-skid braking system example. When you slam on the brakes in a car, wheel sensors instantly detect if the wheel has locked up. If a wheel locks, there's no friction, the car is skidding, and the driver literally cannot steer. The analysis process detects this incredibly dangerous state. It immediately sends rapid on and off control signals down to the brake actuators on that specific wheel. By physically pumping the brakes, the actuator alters the car's physical behavior in real time, allowing the wheel to turn just enough to minimize sliding so the driver can regain control. So to recap, environmental control takes sensory input, analyzes it, and then uses physical actuators to actively control and change the environment.
Section 4. Pattern 3. Process pipeline. High-speed data.
Our third pattern, the process pipeline, shifts gears entirely. It is totally essential for high-speed data acquisition and processing. But before we look at the pipeline itself, we need to define synchronized buffers. Think back to the producer and consumer concept from earlier in your syllabus. In high-speed systems, data is flying in incredibly fast. A synchronized buffer is a shared data space that safely links our sequence of concurrent processes. It allows a producer process, which is collecting the data, and a consumer process, which is analyzing the data, to operate at slightly different speeds without losing any of that critical high-speed data. It acts as a safe, highly controlled waiting room for your information.
Data flows sequentially from left to right. It moves from a producer process through a synchronized buffer and straight into a consumer process. What's incredibly powerful about this architecture is that it allows for extremely fast data processing. Because the steps are broken down into independent processes linked by buffers, each step can execute simultaneously on a separate processor core in a multi-core system. It is basically a highly efficient parallel assembly line for data. The textbook uses a nuclear reactor neutron flux monitor to illustrate this, and it's a brilliant example. In a nuclear reactor, physical reactions happen incredibly fast. Sensors are constantly generating raw analog data about the density of neutrons. This raw data is rapidly pipelined into a buffer, pulled out by an analog-to-digital converter, pushed into another buffer, and then processed to calculate an average flux level before finally being stored and displayed. If this wasn't pipelined, incoming data would literally be lost while the system was busy processing the previous batch. So recapping the process pipeline. It's a sequence of concurrent transformations linked by buffers, and it's perfect for high-volume, high-speed data acquisition.
Section 5. Exam focus and combinations. Let's break the fourth wall for a second and focus on exactly how you need to apply this knowledge to pass your exams and ace your coursework. Examiners love to give you a scenario and ask you to identify the correct pattern. So here is your cheat sheet. You must be able to recognize the right pattern based on its end goal. If the system only triggers an alarm, a display, or a phone call, you are looking at observe and react. If the system uses actuators to physically move, heat, cool, or otherwise change the environment, it is absolutely environmental control. And if the primary challenge of the system is ingesting and transforming massive amounts of high-speed data in real time, you need to write down process pipeline.
But beware of this really common trap. A lot of students make the mistake of assuming a large system only ever uses exactly one pattern. In reality, real-world systems are a total synthesis of these architectures. For example, you might design an environmental control system to manage a chemical plant using complex valves and pumps, but you would almost certainly layer the observe and react pattern right on top of it to constantly monitor those very actuators. If a valve fails to open, the observe and react subsystem detects the failure and triggers a massive safety alarm. They're designed to work together.
Section 6. Summary and next steps. Key takeaways.
Let's wrap up today's explainer by synthesizing everything we've covered so you walk away with a crystal clear understanding. Keep these core concepts in mind as you study. First, remember that unlike object-oriented desktop software, real-time systems are process-oriented. Second, remember the 3 patterns. Observe and react is your go-to for monitoring and sounding alarms. Environmental control takes it a huge step further by using physical actuators to actually change the environment. And the process pipeline safely handles high-speed data transformation using concurrent processors and synchronized buffers. Use the exact textbook examples, the burglar alarm, the anti-skid brakes, and the nuclear reactor to really anchor your understanding of these concepts.
Which brings us to a critical, final question. We've talked extensively today about how to structure these processes, but what actually happens to the system if these concurrent processes miss their strict execution deadlines? What if the anti-skid brakes receive the command even a fraction of a second too late? As we look ahead to our next explainer on timing analysis, I want you to ask yourself how we can mathematically guarantee these systems will react in time. Because in the high-stakes world of real-time software engineering, a late answer isn't just a bug. A late answer is a wrong answer. Thanks for joining me today, and I look forward to seeing you in the next one.